Force vectors. Good day, everyone. Today, we will discuss force vectors, one of the fundamental concepts in engineering statics. Forces are vector quantities, meaning they have both magnitude and direction. Understanding how to represent, add, and resolve forces is essential for analyzing engineering structures and mechanical systems. In this lecture, we will learn vector operations, force addition, Cartesian vectors, position vectors, and the dot product. By the end of this session, you should be able to represent forces mathematically and solve basic force vector problems encountered in engineering practice. Objectives. The objectives of this lecture are threefold. First, we will learn how to add forces and resolve them into components using the parallelogram law. Second, we will express forces in Cartesian vector form and determine their magnitude and direction. Third, we will apply the dot product to calculate angles between vectors and determine vector projections. These skills form the foundation for more advanced topics in statics and mechanics. Scalars and vectors. Before working with forces, we need to distinguish between scalars and vectors. Scalars have magnitude only, such as mass, temperature, and time. Vectors have both magnitude and direction, such as force, velocity, and displacement. Graphically, vectors are represented by arrows. The length of the arrow indicates magnitude, while its orientation and arrowhead indicate direction and sense. Since forces are vectors, both magnitude and direction must always be considered. Vector operations. Several basic operations can be performed on vectors. Multiplying a vector by a positive scalar changes only its magnitude, while multiplying by a negative scalar reverses its direction. Vector addition can be performed using the parallelogram law or the triangle rule. Vector addition is commutative, meaning the order does not affect the result. Subtraction is handled by adding the negative of a vector. These operations are essential when combining multiple forces acting on a body. Vector addition of forces. When multiple forces act on a point, we often need to determine the resultant force. The resultant can be found using graphical methods, such as the parallelogram or triangle rule. Forces can also be resolved into components along chosen directions. When the geometry is known, the law of sines and the law of cosines help determine unknown magnitudes and angles. Understanding force addition allows us to replace several forces with an equivalent single force. Addition of coplanar forces. For coplanar forces, it is often more efficient to use rectangular components. Each force is resolved into x and y components. The resultant x component is obtained by summing all x components, and similarly for the y components. Once the resultant components are known, the magnitude is determined using the Pythagorean theorem, and the direction is calculated using trigonometry. This analytical method is widely used because it is accurate and convenient. Cartesian vectors, 3D forces. In three-dimensional problems, forces are expressed using Cartesian vectors and unit vectors I, j, and k. These unit vectors represent directions along the x, y, and z axes. A force vector can be written as the sum of its components in each direction. From these components, we can calculate the force magnitude and determine its orientation using direction cosines. This approach is fundamental for analyzing forces in space. Addition of Cartesian vectors. Adding Cartesian vectors is straightforward because we simply add corresponding components. The x components are summed together, the y components are summed together, and the z components are summed together. The resulting vector represents the combined effect of all vectors. This component-based method is especially useful when dealing with multiple forces acting in different directions in three-dimensional space. Position vector. A position vector defines the location of one point relative to another. To obtain the position vector from point A to point B, We subtract the coordinates of A from those of B. Once the position vector is known, we can determine the direction of the line joining the 2 points by converting it into a unit vector. Position vectors are commonly used in engineering mechanics to define force directions and moments. Force vector along a line. Many engineering forces act along a specific line connecting 2 points. To express such a force vector, we first determine the position vector between the points, and then calculate the corresponding unit vector. Multiplying the unit vector by the force magnitude gives the force vector. This procedure ensures that the force has both the correct magnitude and the correct direction. The dot product is an important vector operation that produces a scalar result. It can be calculated using vector magnitudes and the cosine of the angle between them, or directly from Cartesian components. The dot product is particularly useful for finding angles between vectors and determining the projection of one vector onto another. These applications frequently appear in statics, mechanics, and engineering design. Key equations summary. This slide summarizes the most important equations discussed in this lecture. These equations include force components, resultant force calculations, Cartesian vector representation, position vectors, unit vectors, and the dot product. Rather than memorizing every equation, focus on understanding what each equation represents and when it should be applied. Mastering these fundamental relationships will make solving engineering mechanics problems much easier.